Okay, there's my balloon. Okay, so we're going to inflate this balloon. Okay, we'll inflate it. Now, when you inflate something, usually if you've got like constant pressure, like if you've got a pump or something like that, as opposed to your lungs, what will I know about how this thing's inflating? Okay, well, for instance, let's actually put some numbers on this. Okay, I have to say a spherical balloon because balloons are not really. In real life, they're not spherical, but unfortunately, because they're not spherical, we can't model them mathematically very easily. So I'm just going to make it a sphere, so that we can. Okay. So a spherical balloon is being inflated at a rate, mark the word, okay, of, what did I put? Let's see. 8 centimeters cubed, 8 cubic centimeters of air per second. So, my question is, if that's how much air we're putting in, what's happening to the radius here? Okay, how fast is the radius increasing? Now, before I finish this sentence, right, I hope you get that, again, and this is a rate question, how fast? Okay. The radius will not be increasing at a constant rate, okay? When will it be increasing fastest? At the beginning, right? Yeah, because it's going to have, a radius of whatever, 0, okay? And then as soon as you put in a bit of air, it goes woof, right? And then that's the exact sound it makes, right? And as you keep on putting more air in at a constant rate, okay, you've got to put increasing amounts of air to keep the radius going and growing and growing and going, right? So, how fast is the radius increasing? And I want it at a particular point in time, okay? Or at a particular position. So, when the radius is, how fast is the radius increasing when the radius is 4 centimeters? I think that's what I said. Yeah, okay, good. So, there's the question. How do you approach it? You want to look at this, and as with so much in maths, the first question is one of translation. Right? So I have a rate up here. I already mentioned as well, I'm going to have a rate over here. That's the question, right? So what information do I have and what am I trying to get? Okay, what do I have? What am I trying to get? Well, I've got this rate here. Now, what's it a rate between? Right? Before we said, you've got d on something and something else. Two things that are changing. What are the things that are changing here? Volume over time, right now, and you can tell that it's going to be volume over time. It's really, really easy. You just look at the units, yeah? So the first unit is a unit of volume, a cubic centimeter, okay? And the second unit is a unit of time, okay? So that's why I've got dV on dt, right? Now it's just equal to 8. As a minor issue, right? When we're looking at derivatives, same deal with integrals. Come in. When you're looking at these, it's a bit like pronumerals. They're unitless. Okay, so dV on dt is not 8 centimeters cubed per second. Okay, it's just 8. Right, and then we deal with units later on. Okay, now that's the first sentence. What is the question? What are we actually after? We're after the rate of the radius increasing. Okay, so this is what we know. So known. What's unknown is radius increases. So that's dr, again, over time, okay? And we want it at a specific position when the radius is 4, okay? When r is 4. Okay, so here's my setup, right? I've got to get from here all the way over to here. So how do I go about that? If I want dr and dt, and I've got dv on dt, you can see the missing component, right, is that I've got no r's here, okay? And you remember, for chain rule, right, I'm going to want dr and dt being equal to something times something. Yes? Now, seeing as there's a dr here and a dt here, there's got to be a dr over something, and there will be a something over a dt. Okay, because these things should be the ones that cancel out. That's what makes chain rule work, right? So because the only other variable I've got is volume, I assume dV goes here and here. Okay, so they'll cancel and give me the dr and dt that I want. Okay. So you look at this versus what we've got. So dV on dt, tick, I've got that. So now I need to work out this part. Okay. So dr and dV, what that tells you is there's some relationship between V and R. As V changes, R changes. So what's the equation? What's the relationship between V and R, volume and radius? Because it's a spherical balloon, right? So you see, careful, they didn't give you this in the question, but they sort of did, right? That the volume that we're interested in is 4/3 pi cubed. Okay, so this is the relationship between V and R that I can use to get to here, right? Now, admittedly, when you look at this is dr and dV. So that means you'd expect R equals something, but I've got V equals something. So I'll differentiate it the other way around. I'm going to find dV on dr, okay? And because it's just a fraction, I can just take the reciprocal once I've got this, okay? So what is the derivative?
4r squared.
Which is the surface area of a circle. If you remember that, the significance of that result from integration, okay? So that's dV on dr, but what I really want is dr and dV, which is just the reciprocal. So now I've got the dV on dt that I had from the question. I've got this dr on dV, and I can put these two together into here, into my chain rule. Okay. So I'd say dr and dV is 1 on 4 pi r squared, and this is just a number, just a constant. It's always 8. 8, yes. So you can see I've got some cancelling. So this will be 2 on pi r squared. And that's as far as I can simplify, right? Okay. If they asked for just a general rate of change, not at a specific point, I'd be finished. But we want it at a place when the radius is 4. So I'd say when r is 4, the actual rate that I'm interested in is 2 over 16 pi, which is 1 on 8 pi. Okay. So like I said, this is a derivative, so it's unitless, okay? So to be nice and neat, I mean, you could get away with it probably just whacking the units on there, but a better way to say it is, the radius is increasing at, and you bring your rate in, and you look at whatever units were supplied to you. So we were talking in terms of centimeters. A radius is just a length, so it's not centimeters squared, which would be area, or centimeters cubed, which would be volume. And the time unit was seconds. Okay, now, usually, right, the difference between this line and this line is quite trivial. You're just adding some words and some units to pad it out a little bit, okay? However, it's going to be quite important later on, which is why I think it's worth putting your concluding sentence. Number one, sometimes your conclusion will be about something getting smaller rather than getting bigger, okay? So when you've got negatives here, that'll make a difference for the conclusion. And secondly, quite frequently, they'll ask you to do something quite different with the units, okay? For example, going from kilometers per hour to meters per second. That's a really common one, okay?